Welcome to the Differentiation of Exponential and Logarithmic Functions podcast. This is an introductory podcast, and we are going to be looking at the derivative of e to the x. And of course, we're going to derive it. But before we do that, let us look at some rules of exponential functions, some properties of exponential functions. We might use one of these properties as we're deriving the derivative for e to the x. All right, so first of all, we have the product rule. And these, by the way, are in your notes. Right, and so if we multiply like bases raised to a power, we add the exponents. We have the quotient rule. Okay. So if we divide like bases raised to a power, we subtract the exponents. We have a negative reciprocal. Right, so a negative exponent is just the reciprocal of that particular function. That particular base, which could be a function. All right, so also, right here we have the power of powers rule in different formats here. So all of these are power of powers. One is just showing you a product. One is showing you a quotient. And the other is showing you a power raised to a power. So technically they're all power of powers because you could say that a and b in the parentheses there is just raised to the first power. Okay, so you can multiply the exponents. So power of powers rule says that if you're raising a product or a quotient or a term that has an exponent on it to a power, right, you're going to multiply the exponents. You're going to apply the exponent to everybody in the product, everybody in the quotient, and then if you've got an exponent already on it, you'd multiply exponents. So here, everybody in the product gets the exponent, and likewise, I can pull that exponent out, right, and show that both terms are, that every term in that product, every part of that product is raised to that power, or every term in that quotient is raised to that power. And then when we have a single term raised, or single terms in a product or quotient that already have an exponent on them, remember to multiply the exponents to raise power to a power. Okay? So just some properties of exponents. Little review of some graphs, just to remind you that as long as the graph hasn't been translated in any way, nothing's been added to the whole function or added to the exponent, that no matter what the base is, the graph of an exponential function is going to go through the point 0, 1. Because right? If you've raised anything to the 0 power, you get 1. And with the exception of 0, you can't raise 0 to the 0 power. And also, if your base is greater than 1, your function's increasing. If your base is between 0 and 1, your function is decreasing. So we have 1 there that's decreasing with a base of 0.5, 5/10, and everybody else is increasing. Although one of them is increasing very, very slowly. Right? So let's derive the derivative for e to the x. Right? So we're going to differentiate e to the x using the limit definition of the derivative. You do need to know how we derive this, and you do know how you need to know in general how to use the limit definition of the derivative to find a derivative, even though we already know how to use some of our shortcut rules, right? You still need to know how to use the limit definition as well. All right, so our first thing is, well, let's use e to the x and write the limit definition, right? So we have the limit as h goes to 0 of e to the x plus h, right? So add a little bit to h as that little bit goes to nothing. So essentially, this is your same function as the average rate of change, except when you take the limit of the average rate of change, you get instantaneous rate of change, which is the derivative. So we're going to take the limit as h goes to 0 of e to the x plus h minus e to the x all over h. Let's rewrite that using the power rule. Right? So just like if we multiply like bases raised to a power, we add the exponents. if we see we've added exponents, we must have multiplied like bases raised to a power. So this would be the limit as h goes to, that is a very strange looking arrow, goes to 0. There we go. That looks a little bit better. Good enough for me. E to the x times e to the h minus e to the x all over h. Right, because if we were to multiply e to the x times e to the h, right, we would add the exponents, and we'd have e to the x plus h, which is what we have over there. So now I notice both of those terms in the numerator have an e to the x. Let's factor it out. So we have the limit as h goes to 0 of e to the x. I give up writing arrows, and they're just going to look like squiggles, times e to the h minus 1 all over h. Let's split this up into two different fractions and two limits. All right, so we're going to put the ones with the h's together and the ones without the h's on the other side. So we have the limit as h goes to 0 of e to the x, and we have times, because that's multiplied, the limit as h goes to 0 of e to the h minus 1. All right, now we look at one of them, and so now we're going to try and plug in. Oops. All over h. So now we're going to try and plug in. Right? So I look at the first one and I go, the limit of e to the x as h goes to 0. I don't see an h. Right? So guess what? There's nowhere to plug anything into. So the limit of e to the x as h goes to 0 is, guess what? E to the x. Right? If you don't have that variable, it's just whatever that function is. Right? There's nothing to plug into. All right, so now we have e to the x. We have simplified one of those limits. Now let's simplify the other limit. Well, let's plug into the other limit. Right? We had no plug-in, so e to the x is our limit. Let's use direct substitution and try that. All right, so if we're going to use direct substitution, right, we just plug in. So we have, I think I'm going to use parentheses instead of that dot. That dot worked just fine when I had a limit there. All right, so we would have times, if I plug in 0, I have e to the 0 minus 1 all over 0. And let's simplify that. Some equals there. All right, so that's going to be equals. We've got now e to the x times, all right, well, e to the 0 is 1 minus 1 over 0. And that would be e to the x over times 0 over 0. And if you tell me that's 0 or e to the x or does not exist, I swear I will cry. Right? This here is the indeterminate limit. And all the indeterminate limit tells you is you can't determine anything from it. That's why it's indeterminate. You can't determine anything from it. And I think I've got some wrong spellings there, but that's all right. I think one of those is supposed to be an E. So you can't tell anything from that particular limit, right? So then we need to evaluate another way. Well, you might be thinking, okay, what tools do I have? Multiply by the conjugate. Now, you can try that, but you're going to get something worse, and you're still going to have an indeterminate limit that you can't fix. And actually, you have no tools in your toolbox right now to be able to work with that limit so you can actually determine what it is. By the end of the year, you will have a tool to be able to figure that one out, but right now we don't have a tool. So we're going to have to try another way, right? We're going to have to go back to looking at it numerically because we don't have any other algebraic technique we can use, right? So we'll look at it numerically and graphically since we don't have an algebraic technique right now, right? And we'll figure out what to do about that indeterminate limit, right? So let's write that down, right? So that we knew that that's what we're doing, right? So here we have an indeterminate limit. We cannot algebraically manipulate the limit of, and that was e to the h minus 1. Actually, let me write in the shorthand. Get rid of that. I don't even need the word the. I just need the limit as h goes to 0 of e to the h minus 1 over h. And I'm going to put in the words yet. So dot, dot, dot. So let's evaluate the limit numerically and see what we think. I hope I have enough room for the rest of my proof here. My derivation. We'll just kind of move these guys over so that I can use maybe that space over there. All right, so let's look at the graph in a table of values. So substituting h equals 0 in the limit expression results in the indeterminate limit form 0 over 0. Thus, we need to determine it another way. And I see that one of my e's should have been an a. All right, well, oops on the spelling. All right, so we can look at the graph of f of x equals e to the x minus 1 over x and observe what happens as x gets closer to 0. All right, we can also create a table of values to either side of 0 and see what number we are closing in on. All right, so by the way, we had e to the h. So we had e to the h minus 1 over h. Same thing, right? The letter doesn't matter. All right, either way, we have e to an exponent and divided by, and in the denominator, the exact same variable. Right? And observe what happens as x gets closer to 0. We can also create a table of values close to either side of 0 and see what numbers we are closing into. So here is the graph. There is a hole in the graph. That's why I put a hole there. And here, if we look at, if you try to plug that into the calculator, right, your calculator will say, problem, right? Because you can't have 0 in the denominator there. So we know 0 is not a value in the domain of that particular expression, but it's not an asymptote, it is a hole. Otherwise, we wouldn't have a limit. And so notice here, if I plug in negative 1/10, we get 0.95, and negative 0.100, we get 0.995, and negative 0.1000, we get 0.999, and on the other side, we get, if we plug in 1,000th, we get 1.0005, and if we plug in 100th, we get 1.005. And so you notice here that on both sides of 0, it looks like we are approaching 1. And that is what we are approaching. So the limit as h goes to 0 of e to the x minus 1 over x, or in our case, since it was e to the h, let's write that. The limit as h goes to 0 of e to the h minus 1 over h is 1. So let's go back to our derivation, our limit derivation, and put that in. All right, so we figured out numerically that the limit as h goes to 0 of e to the h minus 1 over h equals 1. So now let's plug in 1 where we had the e to the h minus 1. So the limit of e to the x is e to the x, because that's an h and not an x. And the limit of, as h goes to 0 of 1, well, that's 1. So now our limit is, so the limit of e to the x as h goes to 0 times the limit of 1 as h goes to 0 is just going to be e to the x times 1, which is e to the x. Well, how about that? We did all that work to get the derivative of e to the x, and we end up with e to the x. Oh, so let's look at the next page. The next page. Come on, the next page. So the derivative of the function f given by f of x equals e to the x is itself. The derivative equals itself. So when you take the derivative of e to the x, it is e to the x. How about that? All that work, and we end up with the very same function, right? When you have more tools, we actually will evaluate that algebraically, just to show you. We'll finish off that derivation algebraically and find out, yes, indeed, that was e to the x. But for now, you'll have to take the numerical proof as part of it and as a part of our justification. And I hope you're okay with that. All right, so pretty easy derivative. It's itself. Let's do one problem, and we're just going to finish off this page of notes. And I think we'll save the rest of the problems for Monday and perhaps later on in the week. All right, so we're going to take the derivative of f of x equals x squared e to the x. This one is a product rule because we don't have to spend a whole lot of time just taking derivatives of e to the x, or if we're just going to get e to the x. So let's add some stuff with it. All right, so remember the product rule is the first times the derivative of the second plus the second times the derivative of the first. All right, so our u here is x squared and our b is e to the x. So the derivative of x squared is 2x. The derivative of e to the x is e to the x. How exciting. All right, so the derivative of this one is f prime of x is equal to the first, which is x squared, times the derivative of the second, which is e to the x, plus the second, which is e to the x, times the derivative of the first. I'm going to put the 2x first. And there we go. We're done. We do have some common factors here, and it would make sense to factor those out if we were then setting this equal to 0 and solving. So for some practice, let's factor those out. The common factors are we have is an x and an e to the x. So we could also write this, and sometimes it's in a different form, so it's good to know both forms. All right, so if we factor out the x and the e to the x, this would just be x plus 2, right? So there's two different ways to write that. Both are correct, but when we get to needing to solve and set this equal to something, particularly 0, it'll be a lot easier if we've gone over a little bit of factoring. And I think that's the last one I'm going to do on this podcast. And let's save the others for class. We'll kind of zoom through them, and then we'll look at some more derivatives of exponential functions. And I'm hoping to finish up quite a bit of this in class. All right, so I think this is going to be the end of the podcast, the end of this podcast. And if I decide to make another podcast on this Nearpod lesson, it'll be right next to this one. But bye for now.